Usually when we want to specify the location of a point in the plane, we use a rectangular coordinate system or a Cartesian coordinate system. And the way that works is we draw our axes and we say, to get from the origin to this point, how far to the right do you have to go? And how far up do you have to go? These two numbers, x and y, these are the Cartesian coordinates or the rectangular coordinates of P. The coordinates of P are x, y. But this is not the only way to specify the location of P using a pair of numbers. A different thing you could do is you could draw this line and let r be the length of that line and let this angle be theta, and then we could just write down the pair of numbers r theta. This pair of numbers is called the polar coordinates of P, and that's another equally valid way to specify the location of P. And sometimes this polar coordinate system turns out to be easier for describing certain shapes. For example, what about the unit circle? Here's a picture of the unit circle. It's a circle of radius 1. It's centered at the origin. Its radius is 1. The equation of this circle using rectangular coordinates is x squared plus y squared equals 1. But what would be the equation of this circle using polar coordinates? This is the equation using rectangular coordinates. If we instead use polar coordinates, then the equation of this circle, the unit circle, is just r equals 1. This circle consists of the set of all points whose polar coordinates are r comma theta and r is equal to 1. Theta can be anything. Theta could be 0, and then we'd be looking at this point on the circle. Theta could be pi over 2, and then we'd be looking at this point. Theta could be pi, and then we're looking at this point. Theta could be 3 pi over 2, and then we're looking here. This circle consists of all points r theta such that it consists of all points whose polar coordinates r theta have r equals 1. The equation of the circle using polar coordinates is just r equals 1. So this is a simpler way to describe a circle. This equation is sort of complicated. This is a very simple equation. Another example is an annulus or a ring, which looks like this. If we're using rectangular coordinates, then the equation of this region in the plane is x squared plus y squared is less than or equal to b squared, and is x squared plus y squared is greater than or equal to a squared. This is how you describe this annulus using rectangular coordinates. But what if we use polar coordinates? Then the description of this annulus is just r is less than or equal to b, and r is greater than or equal to a. That's a much simpler description. Using polar coordinates, this annulus just consists of all points r theta such that r is between a and b. Theta could be anything, and r just has to be in between a and b. Another shape that can be described easily using polar coordinates is what's called a polar rectangle, which looks like this. This inner curve is part of an arc of a circle of radius a. This outer curve is part of an arc of a circle of radius b. And if we're using polar coordinates, then this polar rectangle consists of all points r theta, which satisfy r must be between a and b, r is between a and b, and theta is in between alpha and beta. So alpha is this angle here, and beta is this angle here. So this polar rectangle consists of all points r theta such that r is between a and b, and theta is between alpha and beta. And polar rectangles like this are going to play an important role when we do integration using polar coordinates. Now, suppose we have a point P, and the polar coordinates of P are r comma theta. And suppose we want to find the rectangular coordinates of P. How would we do that? Well, let's draw this line, and let's call this line segment, the length of this line segment is x, and the length of this line segment is y. So the rectangular coordinates of P are x comma y. How do we compute x and y using, if we're given r and theta? Well, from trig, we have x over r is equal to cosine of theta. So that means x is equal to r times cosine of theta. And also from trig, we have y over r is equal to sine of theta. So that means that y is equal to r sine of theta. So these two equations tell us how to compute x and y, the rectangular coordinates of P, if we're given r and theta, the polar coordinates of P. Now suppose on the other hand, we're given x and y, and we want to compute r and theta given x and y. If we square both sides of this, if we square both sides of both of these equations and then add the resulting equations together, we get x squared plus y squared is equal to r cosine theta squared plus r sine theta squared. So that's equal to r squared cosine squared theta plus r squared sine squared theta. And now let's factor out the r squared, and we get r squared times cosine squared theta plus sine squared theta. And from trig, we know cosine squared plus sine squared is 1. So this is just r squared. So we have discovered that r squared is equal to x squared plus y squared. So r is equal to the square root of x squared plus y squared. This is how we can compute r if we're given x and y. And what about theta? If we're given x and y, how do we compute theta? Well, if we divide both sides of this equation by the corresponding sides of this equation, we get y over x equals r sine theta over r cosine theta. And the r's cancel out, so this is just sine theta over cosine theta, and that's just the tangent of theta. So theta is the inverse tangent of y over x. This tells us how to recover theta if we're given x and y.